Okay, so the purpose of this tutorial is to look at solving systems of linear equations, some of the geometric applications and so on that's standard in a first course of linear algebra. So let's begin with the following. So we'll look at the system x1 minus 2x2 minus x3 plus 3x4 equals 0. We'll also impose the equation 2x1 plus 4x2 plus 5x3 minus 5x4 equals 0. And one more. Let's do 3x1 minus 6x2 minus 6x3 plus 8x4 equals minus 3. Let's also change this one, just to make it a little more interesting, to be a 3. Okay, so as is common practice in linear algebra, we'll convert this to an augmented system. So remember, we want to consider a matrix A, a vector x. Here x bar will be x1, x2, x3, x4, and we want to set this to be some vector b, where b bar is 0, 3, and minus 3. So here we see that A has to be a matrix that has 4 columns and 3 rows, so it's a 3 by 4 matrix. The augmented system will be 1, minus 2, minus 1, 3, minus 2, 4, 5, minus 5, and then 3, minus 6, minus 6, 8, and then in the last one we'll have 3, minus 3. Now, some people put a dash here, but that just makes things more confusing, so we'll avoid that. Okay, and we want to row reduce. Okay, so the first goal is to make this entry a 1, but since that's already a 1, the next best thing is to make this a 0. Now, the only way we can make this a 0, remember we have 3 rules. The first one is that we can add and subtract rows. The second one is that we can interchange rows. And the third one is we can scale rows by a non-zero scalar. Okay, so what I'm going to do is I'm going to take 2 of row 1 and add it to row 2. So in this process, row 1 remains the same. So let's just rewrite row 1. I'll also rewrite row 3. Now here we'll have, so we want to do row 2 gets sent to row 2 plus 2 of row 1. So 2 times 1 is 2, so that makes this a 0. That's what we want. If we take 2 of these, I get negative 4, so that also makes this a 0. If I take 2 of negative 1, that's negative 2. Add it to 5, I'll get 3. 2 of 3 is 6, so add it to negative 5, I get 1. 2 times 0 is 0. 0 plus 3 is 3. Okay, so now we have this. Now remember, the goal for the matrix is to have 1s, 0, 0, and so on. Then 0, 1, 0, 0, and then whatever's here, 0, 0, 1, and so on. As a consequence of this, what I'll do is I'll interchange rows 2 and row 3. And so row 1 is the same, but now we have 3 minus 6 minus 6, 8 minus 3, 0, 0, 3, 1, 3. Okay, now what can we do? Well, let's now try to make this entry a 0, sorry. And what we can do is we can take row 2 to now be row 2 minus 3 of row 1. So that does not change the first row or the third row, which is 3, 1, 3. Now we take 3 of that, we get 0. 3 times negative 2 is negative 6, but we subtract it, so we'll get a 0 here. 3 times negative 1 is negative 3, but we're subtracting it, so we add, and we get negative 3. 3 times 3 is 9. Subtracting it, I'll get negative 1. And 3 times 0 is 0, so here I'll just have negative 3. You can see that rows 2 and 3 are scalar multiples of each other. I hate when this happens. Scalar multiples of each other. And so we can just take row 3 to now be row 3 plus row 2. That gives us, well, the first row remains the same. The second row remains the same. And the last row is just a row of zeros. Now, just to clean things up a little bit, what I'll do is I'll take row 2 to be negative row 2, so I'll just scale by negative 1. Okay, so that's about as good as we can make it. So let's now just write it out to get an idea of what the solution set is. So what this says is that x1 minus 2x2 minus x3 plus 3x4 equals 0, and 3x3 plus x4 equals 3. This row of zeros essentially says that the third equation didn't tell us anything, so no new information from the perspective of linear algebra. Okay, so what can we say? Well, from the second one, I can say that x3 is 3, well, let's divide by 3 already. So we have 1 minus 1/3 x4. From the first one, there's no condition on x2. Well, let's actually just write x1 as 2x2 plus x3 minus 3 of x4. Okay, so that's fine. But we can also write this as 2x2 plus 1 minus 1/3 x4 minus 3x4. Now, minus 1/3 minus 3 is the same as minus 1/3 minus 9 on 3, which is minus 10 on 3. So we see that x1 is 2x2 plus 1 minus 10 on 3x4. We see that x2 has no constraints, so x2 equals x2. x3 we've already determined was 1 minus 1/3 x4. And x4 doesn't have any conditions on it. So if there are no conditions on a variable, recall that these variables are called free variables. Oh, still getting used to this pen. Free variables. And these correspond one-to-one to the dimension of the solution set. So we'll talk about this more later, but in particular, since we have two free variables, the dimension of the space of solutions is 2, corresponding to the number of free variables. The ambient space, so we started with 4 variables, so we started in R4. We start in R4. Now we originally imposed, if we look at the original system, we imposed 3 equations. This is 3 equations. But remember, every time we impose a linearly distinct equation, whatever linearly distinct means, we cut the dimension down by 1. For example, if we take start in R2, we impose an equation. Now the dimension is 1. Impose another distinct equation. The solution set is now 0. But if we impose, let's say, start with a linear equation and then start with the same linear equation, then it doesn't cut the dimension down. So what we've determined here is that one of these equations doesn't tell us anything new, because the dimension of the space of solutions is 2. So we went from R4 to R2. We can't draw R4, but we can draw R2. It's a plane sitting inside. So this is a copy of R2 sitting inside R4. And that completes this tutorial, which is it's more of a review, this tutorial, looking at how to solve a system of 3 equations with 4 variables, looking at the number of free variables, and recalling the geometry of the solution set.